Right. So let me just clarify one thing, which I think is extremely important that maybe all of you know. But when people talk about theories of everything in physics, at least, we don't really mean everything. You know, it doesn't mean that we'll have a theory that will predict where I'm going to have dinner tomorrow, or if I'm going to have a haircut, or something like that.
Okay, so it's a theory of some stuff.
It's a theory of some stuff, and it's really relegated to how the fundamental particles of matter interact with each other. Okay, so the notion that we know now is that there are four fundamental forces in nature. Okay, the gravity and electromagnetism that we know, and two others that live inside the nucleus, the strong and the weak force. So the notion of a theory of everything, or a unification, is that we want to bring these four forces into a single force. So that if you look at very, very high energies, i.e. very close to the Big Bang, close to the origin of the universe, you wouldn't see four forces, you would see only one. So that is the pursuit, that if you look at nature at higher and higher energies, hence the interest in the LHC, for example, you would actually start seeing things to look more and more alike, particles interacting in more and more similar ways, all the way up to this unified theory.
So it only looks like four forces because we live in a relatively cold part of the universe.
Exactly. Right?
All right, so Einstein died trying.
He did. He spent, I don't know, 20 years trying to unify only the electromagnetic and the gravitational interactions into a theory in 4 dimensions, as Lee was mentioning there. And people nowadays would say, well, you know, he couldn't have succeeded because he left 2 very important forces out. We now know that there are only 4 forces of nature. And I start thinking, well, how do you know that? Well, that's what we measure. But how do we know about nature? Well, exclusively through our measurements. You know, what we need in order to make sense of reality is our tools. And a lot of discovery in physics, not completely, but a lot of it is very much dependent on the accuracy of our instruments. If you look at the history of quantum mechanics, for example, it wouldn't have happened if we didn't have the right machines, the right laboratory experiments to force people, brute force people into thinking in a completely different way than they were thinking before. It was a real time of drama in physics where the old folks would not want to give up the notion that everything is deterministic and ordered, but experiments forced them into this. Einstein, when he came up with relativity, he had very specific tests of his theory. And eventually, when the tools were allowed, were there, people went out, measured, for example, the eclipse, during a solar eclipse, you could measure stars and look at their position with respect to when the sun is not in the path, and you find a little distortion which has to do with the curvature of space that he predicted would be there. So a lot of what we know of the universe depends on how we measure things. And to me, the problem with the notion of a theory of everything is that it implies that we will eventually know everything there is to know in the world of particle physics only, that we're going to have tools that will be able to give us all the answers that we're looking for. And I do not see how that's possible. For example, let's say we succeed with a 10-dimensional, 11 space-time dimensional superstring theory, which is a wonderful thing, and I'm completely in agreement with Brian that it is about making it falsifiable, making it testable, and that's perfectly okay. What bothers me is not getting there. What bothers me is saying that that is the answer, that is the theory of everything, because very possibly a few years from now, a new machine, as has happened on and on and on in the history of physics, will reveal something completely unexpected that will need new ideas for us to keep going. So for me, physics is a work in progress, is a narrative, is an ongoing effort for us to understand nature.
The endless frontier.
The endless frontier.
And if it's endless, you then can't have a theory of everything.
Right. You make your knowledge grow like an island, you know, but then the shores of your ignorance increase.
Yeah, but
is
what...
this a question of language?
Can I?
Yeah, but wait, but Marcelo,
Wait.
but that sounds like almost wishful thinking. There are things we do understand, and the shoreline of the island does not keep growing. We find another island, but the shoreline of the island we've been studying works, we predict within it, and it doesn't, and we're done. There's certain things about physics that we're done.
We do progress.
But
I mean, you can't
There
claim
are
we don't progress.
It depends how deep your questions are. Okay, so you say, look, Newtonian gravity explains how, how the Earth is going around the sun, everything is a beautiful thing. And then you start to think, okay, but how is matter attracting matter? Well, you say it's the curvature of space, which is what Einstein said. But then you say, but why matter attracts
I'm with
space?
you there. I'm with you there, but hear me out. Hear me out.
Okay.
Using that analog, you have Newton. That works for like horses and stuff. And then Einstein, you need a new understanding that modifies Newton to get high speeds and high gravity. All right? So that's not something separate. That's not a separate island. It's a bigger island with more understanding of the universe, with more tools to measure that fact. I submit to you that it ought to be possible, even likely, that as our tools grow and we discover more things, fine. Then we get to a point where more powerful tools reveal the same phenomenon and not new phenomena.
How do you know
that? Tells, doesn't
I,
that tell you that you hit the limits?
But you can never know that.
Can I try something?
Well, yeah, go.
Because I wouldn't articulate it anything like the way that Marcelo does, but I have a disquiet with the dream of the search for the final theory. And let me try to express my disquiet and see if it overlaps and see if it addresses your question. Physics, the way that Newton taught us to do it, has a certain methodology. And the methodology is we isolate a little small part of the universe and we do experiments on the small part of the universe over and over and over and over again, varying the inputs, or what we call the initial conditions. And by doing this, we learn to separate out what are the generalities, what is true every time we run the experiment. If the experiment is throwing balls up in the air, we can throw them with different initial speeds, different initial directions, but something is always the same. And those things which are always the same we call laws, and we separate them from the initial conditions or the inputs to the experiments which differ. And
the laws are the things that are constant and repeatable
they're constant,
in time and space.
Yes, they're constant and repeatable. And this is the method that Newton taught us, and it's highly, highly successful. It explains the success of quantum mechanics of general relativity, which is always tested, if we're honest, with small parts of the universe and so forth. What is different about the period we live in is that we come to the cosmological scale. And at the cosmological scale, two things happen simultaneously, which I think befuddle us and I think have thrown us for a loop. One of them is we no longer can do experiments over and over again. There's one experiment, which is the universe as a whole. Okay.
The Big Bang is a singular event.
So we're no longer in this place where we can separate out, quote, the laws from, quote, the initial conditions. That's the first thing that happens. And the other thing that happens is the process that Neil has discussed has worked so well that we're left with the question of not just what are the laws, but why these laws rather than other laws? And why the initial conditions, why it turns out that the initial conditions which give rise to our universe are very special. And why these initial conditions rather than other initial conditions. And at the cosmological scale, the method that Newton taught us to discover what the laws are gives us no grounds or no tool to answer the questions, why these laws, why these initial conditions. And at this point, we face a crisis.
Lee,
yeah?
Katie, can't you create initial conditions on a computer and run different universe models? Isn't that tantamount to the same thing?
Yes.
Okay, so here is Lee in his angst that we only have one universe with one set of initial conditions and we're hopeless in a Newtonian sense of being able to experiment with it. But isn't that what you do every day?
No, but we can't understand why these particular laws and why these particular initial conditions.
I think he's heading towards the multiverse.
I'm not heading towards the multiverse.
You are heading towards
I'll give room for other people if other people want to use this.
You are pushing us towards the multiverse.
No.
Multiverse. Katie, what's the multiverse?
Zip it.
Before we head to the multiverse, okay, I think we're at a junction here. And the junction is, okay, the method that Newton gave us no longer tells us how to go ahead. We have two choices. One of them is to ask, what is the right method to go ahead and continue to do science? We have to change the methodology by which we try to understand the universe. That's the first choice. The second choice is the multiverse. The second choice is to say, well, the method we have only works on systems which are small parts of a much bigger entity. So let's invent a much bigger entity that our universe is a small part of and start to reason in the same way that Newton taught us, statistically and so forth, as if there were many, many, many universes. And just to jump in, my take on the multiverse, even having contributed my own versions of it, is that it's the response to taking Newton's method into a domain where it's not applicable and to failing to have the wisdom to invent a new method which is applicable to discovering what the laws are on a cosmological
I
scale.
think just because we don't have an answer to a question yet, for example, why are electromagnetic forces as strong as they are today? Just because we can't answer it now doesn't mean that we're not going to get there. I don't want to have to resort to saying, well, our universe has to have this value or we wouldn't exist, and somewhere over there is a different universe that has different creatures because their electromagnetic interactions have a different strength. I don't think so.
So Lee, I'm going to translate what she just
said.
said. She's saying, just because you can't figure it out,
Yeah.
Oh, no, I agree with her.
doesn't mean the properties of the universe have to be different.
No.
Did I translate accurately there?
I think the conception of laws has to be, let me quote, for example, the first person to think seriously about the issue that I raised, as far as I know, was the American philosopher Charles Sanders Peirce. And he said in 1893 that the progress of science would advance to the point where the problem became not what are the laws, but why these laws. And then he said something I think has a lot of wisdom. He says the only rational way of accounting for why these laws, rather than other laws, is if the laws themselves are the result of a process of evolution. And I think it's that process of evolution that we have to discover and understand, and then we can do what Katie wants us to do.
Marcelo?
I was just want to make a remark before we go into this more philosophical discussion, which is basically we don't even know all the laws, and yes, we're definitely going to make progress. We are always making progress, and there will be answers to many, many questions. But I think it's a process that is not. We should not believe that we should get to an end. You know, I'm for the humility of the humanity. You know, like yes, we're really smart, but to have the notion that we can find not just all the laws that exist in this universe, but also the laws that define the laws in all possible universes, and hence understand this one in particular, it's quite a which doesn't mean I'm a pessimist. I think we should go there. We should totally try. But we should keep in mind that everything should, in the end, be grounded in what we can measure of reality.
But can I just say, Marcelo, that we have had incredibly successful examples of unification. Obviously, certainly, our understanding of matter is more or less unified in an incredibly successful model where we understand that light isn't different from electromagnetism isn't different from weak forces or strong forces. Where do you draw the line? I mean, would you have drawn the line before that great success? Would you have said, we have we shouldn't be thinking about unification with matter, we'll never get there, and it's just too much to expect?
In other words, Marcelo, 100 years ago, what would you have been saying?
I would have been saying that the unification of electricity and magnetism is not perfect, only in empty space. And that is true. If you look at the sorry about this, guys. If you look at the Maxwell's equations that basically describe how electromagnetic waves propagate in space, they are beautifully perfect, symmetric, whenever you don't have any sources of electricity and magnetism. If you look at, sources, they're not perfect anymore. And just to make a comment about this, yes, we have unified, and I think the tendency of unification, of simplifying our knowledge of nature is absolutely key. That's what we all want to do. That's what we'd like to do. And in fact, the standard model, which is what Jana is talking about, is a magnificent achievement in which we can describe everything that we know of particles, in terms of 12 particles, and that's just beautiful. However, it's not a pure unification in the spirit that, say, superstring theory would like it to be, because each one of the forces, electromagnetism, strong and the weak interactions, keep their imprint in the theory. And what we really want in the so-called grand unified theory or gut theory is that these three things become one. And the standard model certainly does not do that. It's really bringing them together in a sort of a patchwork way. And that is, in fact, one of the reasons why we want to go beyond that. That's one of the motivations for string theory.
Jim, have you gone beyond that?
How about
Where are you?
Brian is...
Well, you know, it's been very interesting sitting on the stage and listening to my colleagues. But, you know, and I am far from experimental physicists, as you can imagine. But this is why experimental...
Which means you're a theorist. Yes.
Something like that.
Yeah, okay. It's code for I'm a theorist.
I'm a theorist, exactly. But my point is that it is always the case that it is our experimental colleagues that prevent us from forming a religion, because it is always grounded in what they can measure, as Marcello keeps coming back to. And so although people can express either enthusiasm or dismay about where we are at a given point in time, I think that we need to be a little bit more humble and to understand that the process that we engage in is a constant flight from fantasy about what we would want to happen, and we query nature for that, and that query goes through experiment. So although this has probably been very entertaining for my audience here, I think that at the end of the day, we have to keep grounded in it's got to be about things that affect your lives, and those things are measurable things.
So where has this pursuit taken you?
Oh my God.
Where have you landed?
Why would you ask that?
I'm asking you that here and now. It's New York City. It's March 7th.
Well, partly it's taken to these very strange images that are behind your head right now. These are pictures of equations. I've been, for the last 15 years, trying to answer the kinds of questions that my colleagues have been raising. And what I've come to understand is that there are these incredible pictures that contain all the information of a set of equations that are related to string theory. And it's even more bizarre than that, because when you then try to understand these pictures, you find out that buried in them are computer codes, just like the type that you find in a browser when you go surf the web. And so I'm left with the puzzle of trying to figure out whether I live in the matrix or not.
Wait, you're blowing my mind at this moment. So you're saying, are you saying your attempt to understand the fundamental operations of nature leads you to a set of equations that are indistinguishable from the equations that drive search engines and browsers on our computers?
That is correct. So
wait, I have to just be silent for a minute here. So you're saying as you dig deeper, you find computer code writ in the fabric of the cosmos?
Into the equations that we want to use to describe the cosmos, yes.
Computer code.
Computer code, strings of bits of ones and zeros.
It's not just sort of resembles computer code, you're saying it is computer code.
It's not even just is computer code, it's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s. That's what we find very, very deeply inside the equations that occur in string theory and in general in systems that we can say are supersymmetric.
Okay.
Time to go home, I think. I mean, where are we going to go after? So are you saying we are all just, there's some entity that programmed the universe and we're just expressions of their code?
Well, I didn't say that. Some of those
like the Matrix? That's what you said.
Some of those codes are showing on the screen behind you right now. They don't look like codes, but these pictures, which we call degrass, are graphical representations of sets of equations that are based on codes. So this is, in fact, to answer your question more directly, I have in my life come to a very strange place because I never expected that the movie The Matrix might be an accurate representation of the place in which I live.
Jim, may I give you an argument that we don't live in the Matrix?
Please. Yeah.
A very simple argument.
Give me one now, quick.
A very simple argument. There's a property that the real world right down here has that no mathematical equation has, that no solution of an equation has, that no abstract object has. Here in the real world, it is always some moment, which is one of a series of passing moments. And a mathematical equation doesn't have a flow of time in it. It just is.
No,
and this means...
But Lee...
Wait, let him finish. Wait, I need him here and now.
This means that, to me, that the ancient metaphysical fantasy that we quote are just mathematics cannot be true, because in a world that was just mathematics, there would be no moment of time.
Why isn't
which
there
is this-
math as a function of time?
I'm sorry.
We solve
They're
those.
just-
These are differential equations.
But,
No, but Lee,
then you lay the solution out. X is a... Yeah.
You're mistaking, you keep using the word is, and I'm talking about the word describe. You see, the whole...
Described is fine, but
No,
then,
no,
but then we're
let
not
me
in the
let me
matrix.
finish, please, since
Yeah.
we started with my discussion. The point is that you know, it's fun to talk about some deep metaphysical essence that sits behind physics, but for some of us, it's about trying to find the most accurate way to describe where we live. And so my statement is that in the description of our universe, that is a supersymmetrical universe, which we were going to test in the LHC. If you believe that description, I can show you the presence of these codes. That's my statement.
That's beautiful, and that's fine, and I admire that. Seriously, that's fine. That's another beautiful piece of mathematics that may be explanatory or descriptive of physics, but that all I'm objecting to is that doesn't mean that we live in the mathematics. That means the mathematics is just descriptive of an aspect of the universe. And
Well, that's a
we're
good
not
point.
in
Let
the
me follow
matrix.
that one up. Jim, just because, who was it? Eugene Wigner, who commented on the unreasonable effectiveness of mathematics that we just invent in our head, yet the universe follows, can be described mathematically. Mathematics is the language of the universe. Brian, math is your tool. So should we be amazed or depressed by what Jim tells us here?
I can't really comment on what Jim says. I find myself in the unusual position of feeling rather conservative on a panel when usually I'm sort of at the outskirts of
And by the way, the pictures Jim showed all look like spirograph images
I saw them.
from your
and
kids'
I don't
thing.
know enough about them to comment, but there is an interesting question, the one that you raise, about whether math is descriptive of the universe, or we are the math, or what's the role of math? Do you discover it? Is it invented? I mean, I had a conversation, and I think you may have been involved in it, if not mistaken. The question was, is math the right way of going about trying to find deep physical law? And I said, look, I can imagine one day we'll encounter aliens, and they'll say to us, okay, show us what you've got to describe the universe. We break out our mathematics, and they look at it and they say, oh, math, we used to do that.